Hi, I'm Kuba, and welcome back to Bielik Anatomy. Over the past 6 episodes, we've implemented every single Triton kernel we need. RMSNorm, MatMul, Attention with Rope, Flash Attention, and SwiGLU. Today we are going to put it all together and actually talk with Bielik. Let's get to work. If we load the Bielik 1.5 billion Instruct model from HuggingFace and print out its architecture, the structure is clear. We have embeddings, then 32 decoder layers, then a final norm, and the LM head that projects to vocabulary. Each decoder layer has attention and MLP block. What caught my attention is that Bielik uses bias in the query, key, value, and output projections, and in all the MLP layers. So right away I knew I would need to handle bias in my kernels. We'll get to that in a minute. But first, there's one thing missing from our previous episodes: the embedding kernel. So let's start with that. Let's walk through the code. We set up a two-dimensional grid. Program ID token handles the specific token, and program ID chunk slices the large embedding vector into manageable pieces. First, we load the token ID. Then we do some simple pointer math. We multiply that ID by the embedding dimension to find the exact row in our weight table, and do the same for our output destination. Finally, we load our specific chunk of data and store it. Notice the mask that keeps us from reading out of bounds on the last chunk. Now I will be honest. PyTorch's embedding layer is actually faster than my Triton version. But I wanted to understand how every piece works under the hood. And the performance difference is tiny compared to the massive MatMul and attention operations. Next up, all those liner layers in the decoder: query, key, value projections, output projection, gate up and down projections. And they all have bias. This means we need to extend our MatMul kernel to handle bias as well. To do that, we first pass the new bias pointer and a compile time boolean flag directly into our kernel signature. Then inside the kernel we check that flag, load the bias row into memory, and broadcast it directly across the rows of our accumulator matrix. The beauty here is that the bias addition happens right in the registers, using the same floating point 32 accumulator we use for the matrix multiplication. So there is basically zero performance cost. We get the fusion completely for free. Plus, because we use a compile time flag, if a certain layer doesn't need bias, we just set has bias to false. The bias code literally vanishes from the compiled kernel, giving us zero branching overhead. Then I got to the feed-forward network block, and the same story. The gate and up projections both have bias. My original SwiGLU kernel didn't support bias, so I need to add it. We start by modifying the kernel signature to accept pointers for both the gate and up biases, alongside our compile time optimization flag. Then, right after computing the matrix multiplications, we conditionally load both bias vectors into SRAM and broadcast them straight into our floating point 32 accumulators. It's the exact same approach. We use the has bias flag to keep it free of branching overhead. When enabled, we load both bias vectors and fuse the addition right into the registers, right before applying the SwiGLU activation and multiplying the gates together. Now, with all the kernels ready, I could finally build the decoder layer. It's actually quite straightforward. Each layer does RMSNorm, attention, residual add, and then RMSNorm, feed-forward network, residual add. Look at implementation. In the attention block, we do query key value projections with our MatMul Bias kernel, reshape to multi-head format, and apply rope. Then, flash attention handles the actual attention computation with grouped query attention. Bielik uses 12 query heads, but only 2 key value heads, so we get a 6 times reduction in the key value parameters. After attention, we have output projection with bias and residual add. The feed-forward network block is even simpler. We do RMSNorm, fuse SwiGLU, then down projection with bias and residual add again. The full model is just stacking these pieces together. Embeddings go in, we pass through 32 identical decoder layers, final RMSNorm, then project to vocabulary with the LM head. We also need to build the rope cache once at init. We precompute the cosines and sines values for all positions up to the maximum sequence length. Then, during forward passes, we just look up the values we need. For generation, we have basic autoregressive sampling without key value cache. You can go greedy for deterministic output or sample for more creative responses. Before we can test our implementation, we have to download model from HuggingFace. To do this, we accept the conditions on HuggingFace and download the model. Now it's the moment of truth. I built a simple chat interface where you can talk to Bielik interactively. I loaded the pretrained weights, initialized the model, and tried generating some text. And it really works! All those Triton kernels working together. Obviously, I had to benchmark it against PyTorch. Let's look at the forward pass latency first. Across different sequence lengths, our Triton kernels are consistently faster, averaging at 11% speedup and peaking at 20% for 256 tokens. At really short sequences, both implementations hit a 20 millisecond latency floor. That's just kernel launch and structural overhead. And at longer sequences, we simply hit the memory bandwidth wall of my RTX 4060. But what about text generation? Here's the cool part. Our time to first token is at 28% faster than PyTorch. That is a clean, measurable win for our custom kernels. However, for overall generation throughput, we are hitting about 49 tokens per second, which is only a 5% bump over the PyTorch baseline. Memory usage is exactly the same for both, around 3 GB. So why only a 5% speedup in total throughput? One massive reason: we don't have a key value cache yet. Right now, for every single generated token, we recompute attention for the entire history. It's an n-squared computational nightmare that completely swallows our kernel level gains. But for a first working version built entirely from scratch, it works. It's measurably faster in TTFT and it actually talks. And that key value cache bottleneck? Well, it sounds like a perfect problem to solve in the next episode. Over this series, we've built a 1.5 billion parameter language model architecture from scratch using our own Triton kernels. But honestly, we're just getting started. See you in the next episodes. And thanks for watching. Bye.